Today we're going to do a lab in which we're going to try to verify the thin lens equation. If you remember the thin lens equation we learned last week, it says 1 over F is equal to 1 over DO plus 1 over DI. We've used that a lot. You've trusted me that it's valid. You've trusted me that it's correct. Today we're going to try to show, in fact, that it is correct so that you don't have to trust me anymore. The problem of this lab, always phrased in the form of a question, is the thin lens equation valid for a particular thin converging lens? Because, of course, you're using one particular lens, not all of them in the world. So when we verify this, we're actually verifying it for your lens as opposed to all of them. But that's good enough for us today. 3 sets of variables again. The manipulated variable, there's one of those, and you'll see what that is in a few minutes. Same deal with the responding variable. There's one of those, and you'll see what that is in a few minutes. The control variables, there's lots of them. There's 1 or 2 control variables that are particularly important to get. There's lots of others like the temperature of the room, the humidity of the room, and whatever that I don't really care about so much because you're not going to list 1,000 different control variables. I want you to get the one or the ones that are particularly important, the ones that are critical, all right? So what's this lab going to look like? You're going to have an apparatus that's called an optics bench apparatus, which actually consists of a number of different parts. You can see the diagram or the picture of it there. This optics bench apparatus consists of a meter stick, and it consists of 2 meter stick holders. It also consists of a screen, which is really just a cardboard cutout, and a screen holder. It also consists of a candle, which is going to serve as your object, by the way. And of course, we've got our candle holder. And then finally, it consists of a convex or converging lens. And then, of course, we've got our lens holder. So all of these things which really make up this optics bench apparatus. My suggestion for you when you're doing this lab is to snap a photo, snap a picture of it. You don't necessarily have to include that photo in your write-up, although you can if you want. But what the photo does for you is helps you to remember. It's a little checklist, right? It helps you to remember what you used. When you go back and you go to write up your lab later on, you'll look at it and say, oh yeah, I forgot about that. You're not going to forget if you have a picture in front of you. Now, before I flip the page, I want to show you how this works. I'm not going to give you the procedure right now until I flip the page, but I want to show you how it works. You're going to, first of all, you're going to do a couple of things first before you even set it up like this. But once you get it set up like this, you're going to want to make sure you put the candle at the end of the meter stick, and you're going to leave it there. Okay, some people in the last class didn't catch that little thing that I had mentioned to them. I said the same thing to them as I am to you, but some of them missed it. Okay, you want to put the candle at the end of the meter stick. Now, in the end, what you're going to do is actually change the position of the lens. You're going to change the object distance, right? The distance between the object and the lens. But you're going to do that by moving the lens back and forth as opposed to moving the object back and forth. It doesn't really matter which one we move. What matters is if we want the object distance to change, then we move one of the lens or the object. So put the candle, the object at the end, and then move the object. Then the screen is also going to be moved back and forth in order to find a good, clear, sharp, focused image. So you put your object at the end, you put your lens somewhere 20 centimeters away from it, and then you're going to have to move your screen until you see a good, sharp, focused image of the candle, or of the flame, I should say, on that screen. The procedure is going to be as detailed here. By the way, you're not going to have to write out the procedure, so you want to just snap a photo of this or whatever you got to do, okay? You're going to set up the optics bench apparatus as you saw in the diagram just a minute ago. You're going to determine the focal length of the lens by focusing on a far-off object through the lens onto a screen. That's basically what we did the day in class when we had the Canada flag up on the board. You remember that? We tried to focus an image of that Canada flag onto the screen, except you guys are going to be aiming at something further away. Maybe aiming at the condos across the street. Maybe walk down the hallway to the end of the hallway and focus on the flags on the other side of the football field. Aim at something farther away than we did in class that day. Now, if you see a good, clear, sharp, focused image of that object, whatever it is, an image of that object on your card, then measure the distance between the lens and the card, and that will be your focal length. Now, a couple little tricks here. As I said, you want to be focusing on an object that's far away as you can. And secondly, you want that object to be bright. So in other words, you don't want to focus on something that's black. Okay, you want it to be something that reflects a fair bit of light. And thirdly, you want to be somewhere where it's fairly dark. So ideally, you got some lights flipped off in the classroom. You're aiming at the condos across the street or whatever it is that's reflecting quite a bit of light, but you want to be in a relatively dark room. Anybody want to suggest to me why you want to be in a dark room as you do this? Light comes through the lens, forms an image on the screen. If you have too much light from the lights on the ceiling, then that image gets washed out. You don't end up seeing anything, right? We don't want the ambient light to get in the way of the light that's coming from the object. So you want to be in a dark room, but you want to focus on something that's further away. So you get the focal length. Now, you want to place the object at a distance greater than the focal length of the lens away from the lens. So you want DO always, in every trial, DO is going to be bigger than F. If your focal length is 10 centimeters, make DO 15. If your focal length is 15, then make DO 20, 25, 30, whatever. But remember, you're doing that not actually by moving the object, you're doing that by moving the lens. Bottom line is you want DO to be bigger than F. Then you want to move the card back and forth on the other side of the lens until you see a good, clear, sharp, focused image. When you do, record that distance as DI. So this would be DO, and then this one would be DI, assuming you saw the picture of the flame on that card. And then, of course, you're going to repeat it 10 times so that you have 10 different sets of data for object distance and image distance. One focal length, maybe it's 10 centimeters, maybe it's 15. It's going to be somewhere in that range of 10 or 15 likely. By the way, what's the image going to look like? Well, the image on the right, you can see, I think you can see it from where you are. It's kind of a circle. The image on the left is kind of an upside down flame. This is what we want. This is not what we want. Light will always go through the lens. You will always see light on the card, but that's not an image. If you're trying to produce an image of a flame, then the image should look like a flame. It shouldn't just be washed out light. So this is what you're looking for, right? Sometimes it might be bigger, sometimes it might be smaller, inverted, whatever, but it should look more or less like that. All right, once you get your data table completed, object distance, image distance, then you're going to want to create another table, an analysis table, which is the inverse of the object distance and the inverse of the image distance. So literally, you're just flipping them over. You can do it with your calculator, 1 over DO, or you can enter that formula into a spreadsheet and have the spreadsheet do the calculations for you. Once you have that table completed under analysis, then you're going to plot a graph. And this graph is going to be 1 over DI versus 1 over DO. Now, pay close attention to this one. This graph will be a straight line, just like all the other graphs that we've done this year. But it'll be a straight line that looks something like this. It's a negative slope. There is a y-intercept for the first time in any of the graphs that we've done this year. Same strategy for analyzing this graph, though, as for all the other ones. You want to get an equation from the graph. From the graph, it's always, for a straight line graph, y equals mx plus b. Replace y with whatever appears on the y-axis. Replace m with slope. And replace x with whatever appears on the x-axis, which is 1 over do. But notice in this case that we can't just arbitrarily get rid of the y-intercept because there is clearly a non-zero value for the y-intercept. Let's get an equation from your data sheet that matches up with this. 1 over di, 1 over do. How about this one? Rearrange it to take the same form. To solve for 1 over di. I'm actually going to rearrange it, go one step further in the rearranging of it. Say 1 over di is equal to negative 1 over do plus 1 over f. The reason I went one more step is because I want it to be in the same order that it appears here. All right, cross off things that appear in both. 1 over di appears in both. 1 over do appears in both. What are we left with? Slope is equal to negative 1 times 1 over do. So the slope is equal to negative 1. Regardless of which lens you use, your slope will be negative 1, or at least theoretically it'll be negative 1. It may work out to be something slightly off of that, but it should work out to be very, very close to negative 1. If your focal length, Jotham, was 10 and your focal length was 17, your slope will be negative 1 and your slope will be negative 1. Doesn't matter what lens you use. So this isn't going to be helpful to us if we all have the same value of slope regardless of what our data looks like. For the first time, we're going to start using the y-intercept. The y-intercept is 1 over the focal point. Rearrange that, and we get f is equal to 1 over b. This is what we want. This is what we're going to use. We already measured the focal point, focal length. We already measured what it was supposed to be. We recorded that right at the beginning of the experiment. Now we're calculating the focal length. We want to compare these two values. And if these two values are the same, then this lens equation must be valid. Here's why. I assumed that the lens equation was valid, right? All of this stuff that I did here assumed that 1 over f is equal to 1 over do plus 1 over di was valid. Right? I used that equation on both sides. I assumed that it was valid. If the focal length that I calculate right here is the same as the focal length that I measured originally right here, if they're the same, then my assumption must be correct. Does that make sense? The assumption that I made that that equation is valid, it must be a correct assumption if I got the same value for the focal length as I think I should have gotten. How do you know if you're close enough? Because reality is it's probably not going to be exact, right? Calculate a percent difference. Right, we've done that before, right? Percent difference, actual minus theoretical over theoretical times 100. If you're less than 10%, okay, it all works. If you're more than 10%, then we'd say the lens equation was not verified. And it's not valid for that particular lens. Conclusion, is it verified? Is it valid for a particular thin lens? How do you know? Your justification is basically a 1 or 2 sentence statement of what we just did, right? The analysis that we just did. And then, of course, your sources of error. List a few good sources of error, plus corresponding suggestions for improvement. We don't necessarily, when we say suggestions for improvement, we don't necessarily mean things that are going to fix it completely, but things that would make it better. I was talking to one of my Physics 20 students over lunch hour. They just completed a lab on circular motion. You guys remember that one where you swung the rubber stopper around? And he was thinking about friction between the string and that PVC tube that you were swinging around. I said, that's a good one. Okay, there is going to be friction there. He says, yeah, he says, I was thinking maybe I could put some kind of lubricant on the top of it to maybe make it less friction, but that's not going to fix it. I said, that's okay. That's going to make it better, right? That's better than having more friction. Less friction is better than more friction. So your suggestion for improvement doesn't necessarily have to solve the problem. It needs to improve it. That make sense? Okay, what do we got to hand in here, guys? You got to hand in your problem, of course, which I already gave you, your variables, which should have became somewhat evident as we were going through the procedure for that. You need to hand in your data, of course, which is your DO, DI, and F. Your analysis, which is your 1 over DO, 1 over DI, and then your graph, and then analysis we did based on the graph. Conclusion, and your sources of error.